Okay, today we are going to learn about eddy currents and its application. Eddy currents and its application. So some desirable application and some undesirable application. Now we just start what is eddy current. Eddy current. So eddy currents are the currents which flows in a thick conductor. In a thick conductor, whenever magnetic flux linked with it changes. So if you have a thick conductor and the magnetic field linked with, the magnetic field applied in its surrounding vicinity is either increasing or decreasing, then magnetic flux linked with the thick conductor will change. And whenever there is a change in magnetic flux, an induced EMF is produced. The direction of induced EMF is given by Lenz rule. You can determine what should be the direction of induced current. Induced current will flow in such a way that it will oppose the reason, the very cause which produces it. So that you have to determine. So then eddy currents are the currents which flow in a thick conductor whenever magnetic flux linked with it changes. So the condition is conductor should be thick. If it is thick, then its resistance will be low and current will be large. And if it is very thin, then its resistance will be high and current produced will be very low. So see the scenario. If you have a pole pieces magnet like this type of magnet, and you have a metallic conductor, okay, suppose this is north pole, this is south pole, and this metallic conductor is moving. If you oscillate it, say this is suspended, and just oscillate this thick conductor, you will find some current is produced in it, and the motion of oscillation of this thick conductor is opposed. If you oscillate it within poles of a magnet and magnetic field, then what you see, some eddy current is produced, and this eddy current will oppose the reason. The reason is the oscillation of this plate, and eddy current will oppose that oscillation. So the oscillation will be damped out and immediately it will be stopped. This phenomena is used in dead bit galvanometer. Because in galvanometer, if a thick conductor, say this is a thick conductor, and this thick conductor is oscillating in magnetic field, I can show you. Say, if you have applied the magnetic field north pole from this side, south pole, this is full magnet, and if you keep on oscillating like this, okay, so just oscillate it. So then what you observe after a few seconds, the moment you switch on the magnetic field, this will stop immediately. So why it will stop immediately? The reason is, since when it is coming out of the magnetic field, then flux linked with the coil, this plate will change, because the area of the plate inside the magnetic field will decrease. And so flux, which is phi is equal to B into A, since decrease in A will cause the variation in flux, magnetic flux, and that change in magnetic flux will induce the current. And this current will flow in such a way that it will oppose the reason. The reason is, if this plate is coming out of the magnetic field, then it will oppose it. So what will happen? It will try to go inside, and when it is going inside, then also it is opposed. So what will happen? Oscillation will die out immediately. Okay. So this is the application of eddy current. Now eddy current, you can see the application of eddy currents. One of the application is in dead bit galvanometer. Dead bit galvanometer. Now you have already studied galvanometer, moving coil galvanometer. There the galvanometer, one spring is, coiled spring is there. So when current passes through the coil of galvanometer, what will happen? The coil will experience a torque, that is deflecting torque, and at the same time the coiled spring will provide the anti-torque. So meanwhile the equilibrium, before the equilibrium will is established, the coil keeps on oscillating like this for few minutes. You may say 30 seconds, 15 seconds, and it will be difficult for you to take the reading, because if the pointer is oscillating like this, how can you take the reading? How can you take the reading? This is a problem. So if you want to stop it immediately, then that coil should be wounded over a metallic frame, and that metallic frame, because of the change in flux linked with the metallic frame, some induced current will produce, that is eddy current will produce, and this eddy current will oppose the oscillation of the coil. So immediately the coil will come to the rest. So the coil will immediately come to the rest. I mean, if it deflects like this, then it will remain at this position only. But in the absence of that metallic frame, it will keep on oscillating for some time, and then it will be difficult for you to note the reading. That's why. So this is used in dead bit galvanometer to stop the coil of galvanometer, which was keep on vibrating, I mean oscillation. So just to stop it, magnetic field is that metallic frame is there, and that metallic frame induced current is produced, and that induced current will oppose its oscillation and brings it immediately into the rest position. Now the second application is induction furnace. Induction furnace. Details you just know. Sometimes in board examination question will come like what are the application of eddy current. I mention few application of eddy current. Then you have to mention these things. Then you have to write 4 or 5 lines. What I told you just now, you have to write. Because if I start writing this explanation, then it will take too much time. So induction furnace. Induction furnace, if you want to make alloys, okay. So different metals are kept inside the magnetic field, and the magnetic field is such that it keeps on varying. You can do it by applying a coil, and through which a current is passing, and that current, if you keep on increasing, then magnetic field of the coil will also keep on increasing. And due to change in magnetic field, magnetic flux linked with the pieces of metals, that also increases or decreases, whatever. So then what will happen? Eddy current will produce, and because of large eddy current, heating effect will be there, and heating effect is so high that metallic pieces will be melted out, and then different metallic pieces, when melted, it mix up and forms alloys. So this is a way to form alloy. Other use is, if you want to melt a that is big log of metal, then put it inside magnetic field, and then vary the magnetic field by some means. You have some bearing current, allow it to pass through the coil. Then what will happen? Because of the varying current passing through the coil, magnetic field at the center of the coil will also change, and due to change in magnetic field, what will happen? Flux linked with the metallic sheet will change, and that because of that eddy current will produce, and eddy current produces heating effect, and if the heating effect exceeds, I mean its temperature above the melting point, then what will happen? The whole metallic log will melt. So this is the another way to melt a metallic log. So this is called induction furnace. You might have studied blast furnace, okay, in the extraction of metal like iron, blast furnace. But there coal is burnt. But here no need to burn the coal. So apply the flux, I mean varying current, I mean current through the coil. So that produces varying magnetic field, and magnetic field linked with the thick sheet or thick metallic log, that will also increase. So increase or decrease in magnetic flux with the metallic log will cause eddy current, and that eddy current produces heating effect, and because of that heating effect the temperature of the metallic log goes beyond its melting point, and melting of that metal will take place. Okay, so this is the another role of eddy current used in induction furnace. Now the third is induction brake. Induction brake, especially the train which is operated on electric current. So in that train, between two rails, some electromagnets are provided, and that electromagnet, whenever driver wants to stop the train, now some switches or some controls are there with the driver. The moment he just on the switch, what will happen? Current through the electromagnet, I mean electromagnet becomes active, and because of the high magnetic field provided by the electromagnet, the wheels, which is metallic, which keep on rolling over the rail, now the magnetic flux linked with the wheel changes, and so eddy current is produced in the wheel, and that because of that eddy current it will oppose the reason. Reason is movement or rolling of the wheel, so it will stop that rolling, and that's why it is used in induction brakes. Induction brakes. So application of eddy current. Now the fourth application is, yeah, electromagnets are placed near the rails, I mean just near the rails, between two rails, okay, track, and then the moment wheel goes in between, then magnetic flux linked with the wheel will change, and because of that magnetic flux linked with the wheel changes, so eddy current will produce. Whenever there is a change in magnetic flux, then current will produce, and because of that eddy current it will oppose the reason. Reason is rolling of wheel, so that will stop the wheel. So I mean, in other words, anti-torque will act, that will stop the rotation of the wheel. Okay, so this is the application in induction brake. Now the fourth one is diathermy. Induction brake. Suppose you have two rails. These are rails, okay, and wheel keep on moving over the rail. Now, if electromagnets are provided here, then and varying current is passed. So because of that electromagnet, or suppose magnetic field is there. So when the wheel is passing through the magnetic field, the area of the wheel inside the magnetic field is decreasing, because wheel is going like this. So area of the wheel will decrease, or the flux linked with the wheel will change, because different area of the wheel is coming inside the magnetic field. Different area, because sometimes suppose magnetic field is along this direction, and something is revolving, something is rotating, a disk is rotating inside. So magnetic field first link with this area, and then this area will go, again new area will come, again new area will come, and that area is changing every time. Suppose magnetic field is along this direction, and your wheel is rotating. This is your wheel. So every time this portion of the wheel will come into magnetic field, and then what will happen? Because of its rotation, now this area is going out of the magnetic field. So flux linked with this area is changing, and because of change in magnetic flux, so some induced current will produce, and again the new area will come within the magnetic field. Again same thing happens with this area. Again same thing happens with this area. So no, why current is lost? Okay. So when it is moves out, for some time it is current is there. So because of that current that opposes by that current, what is the nature of that current? According to Lenz rule, it will oppose the reason. So reason is rotation of the wheel. Wheel is rotating about its axis. So magnetic flux will change, and because of the eddy current it will oppose the rotation. So within few seconds it will stop. It will stop. I have that type of apparatus in my laboratory. I can show you, but nowadays not possible. So that's why this is the phenomena. Now in diathermy is a dip heat treatment. Some persons may suffer from muscular pain. So they need to apply dip heat radiation therapy. And in that case, diathermy treatment, eddy current is used. So some metallic plate is placed inside the body of that person whosoever is suffering from muscular pain, and magnetic flux applied across that plate is changing. I mean magnetic field is changing, because of that magnetic flux will change, and so induced current will produce in that metallic sheet, and because of that induced current, heating effect will there, and that heating effect will penetrate your muscle. I mean heat will penetrate your muscle, relaxing you from muscle pain, I mean muscular pain. So that's why in diathermy treatment, physiotherapists are using this type of device. So this is based on the application of eddy current in diathermy treatment. Diathermy treatment. Diathermy treatment. Okay. Now the fifth one is, this is not the part of diathermy treatment. Now I can rub this portion. And the fifth part is, in diathermy treatment, deadbeat galvanometer, induction brake, and induction furnace. And more than that, you can study from other books. You will find some more applications are there. In a speedometer, or electric meter. You might have seen electric meter, one disc is keep on revolving, keep on rotating about some axis, and that is rotating due to the eddy current. That metallic aluminum disc is rotating, and because of this rotation is due to the eddy current. Now in a speedometer, you might have seen in vehicles that is speedometer, which is used to measure the instantaneous speed. So that also works on the phenomena of eddy current. So one metallic sprinter type things is revolving inside the cylindrical magnet, and the flux linked with this is changing. Because of the change in flux, eddy current is produced, and that eddy current is coming to the meter, that is a type of galvanometer is connected, and because of that current, deflection occurs. So this is used in a speedometer also in vehicles to measure the instantaneous speed. And some more magnetic brakes we have discussed, power motor, just enough, 5 application. So in deadbeat galvanometer, induction motor, induction brakes, diathermy treatment, and speedometer. Now you can do this experiment if you have a solenoid. Suppose if you have a metallic, say soft iron that is a cylindrical, and a coil is wounded. Okay, and here is a battery and a switch. If you place a metallic coin, this is a metallic coin placed over it. The moment you close the switch key, what will happen? A current, growing current, because of self-inductance phenomena, a growing current starts flowing through the coil. It's a solenoid. Okay, some metallic piece is inserted. I mean iron piece, iron rod is inserted to get confined the magnetic field. Now, because of this current, because of the growing current, magnetic field inside the solenoid that also keeps on changing, increasing, because the current is growing. So when the switch was open, no current is flowing. So magnetic field is zero. But the moment you close the switch, one current starts flowing through the solenoid. And because of self-induction phenomena, it will take few seconds to get its maximum value. Okay, so magnetic flux linked with the coil will change. Now see, one disc, metallic disc is placed over it. Coin, you might have seen coin, iron coin. So it is placed over it. Then this coin will have some magnetic field, because the magnetic field of the solenoid. So because of changing magnetic field, so the flux linked with the coin will also change. And then what will happen? Eddy current will produce. And that eddy current will be such that it will oppose the reason. So what is the reason? The increasing magnetic field. And magnetic field of the solenoid will be in what direction? Yeah, tell me. Magnetic field will be along. So if this is north pole, suppose this last turn is north pole, then the lower face of the disc will acquire the same pole, north pole. Because if it is north pole, then north pole means magnetic field is along this way. So the disc will have the magnetic field in the opposite direction, because the magnetic field of the solenoid is increasing. So how will it oppose? How will it oppose the increase in magnetic field? By applying its own magnetic field in opposite direction. So then lower face of the disc will have north pole, and then what will happen? North will repel the north, so the disc will thrown away. The disc will thrown away. The disc will thrown away like this, and the current will also be in anti-clockwise direction. Current. These are the currents. Because when the current passes through a solenoid, what you have studied in solenoid, so if you are allowing current to pass through it like this, then each turn of the solenoid will behave as a current carrying loop, and current carrying loop behaves as a short dipole. So this side it will be south, and the back side will be north, south, north, south, north, like this. So it will behave as a magnet. Then one side will be strong north, one side will be strong south. Suppose this pole has north, then since the magnetic field of the solenoid is changing. Why it is changing? Because of self-induction phenomena. Self-induction, what is self-induction? The property of a coil by virtue of which it opposes the growth and decay of current. So since the current is growing, so it will oppose the growth. Okay, that's why it takes few seconds to get its maximum value. Okay, during that time interval, magnetic field of the solenoid is changing, that is increasing. So then current induced, eddy current induced in the disc will be such that it will oppose the reason. So if the magnetic field of solenoid is along this direction, then magnetic field of the disc will be along this direction. So then only it will be two vector quantity in opposite direction, the net will be minus. So it will be less. So this will oppose. So at the same time, and after few seconds it will come down because of the weight of the disc. Okay. Now, if you break the circuit, then also it will again thrown up. So at the time of break of circuit, then this will be south. This end will be south. Then the lower end of the disc will be again south. Then south will repel. So repulsion will take place. So current will flow in such a way that lower part will have always, that is lower face of the disc will have always similar type of polarity. Whatever the polarity of the solenoid of this and the same polarity will develop to the lower face of the disc. And what will happen? Because of that, repulsion will occur and the disc will be thrown away. It's a very simple experiment you can perform at your home also. But remember, you have a current carrying, a battery of high EMF. Then only you will observe this type of phenomena. In laboratory, I can show you experimentally ring launcher, how the ring is getting launched when a bearing current is passing through the solenoid. Okay, so these are the experiment based on eddy currents. Now, undesirable effect is because of eddy current, heating effect is there, and that heating effect will cause the burning of the coil. That will destroy the insulation of the coil, and the circuit gets short circuited. So because of that, the appliances becomes useless. Sometimes the transformer, the coil of the transformer burns because of the excessive heating effect. And that excessive heating effect is produced by the eddy currents. Some way is there through which you can minimize it. So to minimize the eddy current, the area, this rectangular, seat is cut in such a way that this area can be reduced. So I am showing you the next diagram. Take the snapshot. Okay. Taken. Application of eddy current. Application of eddy current. Yeah. Huh. Then no, this is simple experiment to demonstrate how eddy current works. Experiment to demonstrate. Okay? Experiment to demonstrate. Experiment. Ring launcher is just to demonstration of eddy current. It's a demonstration of eddy current. If you remember, I have shown in school many times in class, in laboratory. That is a ring launcher. So experiment to demonstrate, all because of eddy current. Experiment to demonstrate the phenomena of eddy current, the effect of eddy current, effect of eddy currents. You have some other phenomena also. I am showing you the other phenomena. If you have a pipe, metallic, one is hollow metallic pipe, other is PVC pipe of same thickness, okay, same length, hollow. And if you have a cylindrical magnet, and the diameter of cylindrical magnet is little bit less than the diameter of this pipe, so that if you allow the cylindrical magnet to pass through this pipe, it can pass easily without touching the side of the wall of the cylindrical pipe. Okay. Now, if you have a cylindrical magnet and this cylindrical magnet is allowed to fall in a freely falling condition like this, then say it is taking 1 second or 2 seconds to cover the site. Okay. But if you allow the same magnet to fall through PVC pipe, this is PVC pipe, and this one is metallic. Okay, metallic pipe. Metal may be aluminum, metal may be your copper, and allow a cylindrical magnet, okay, small magnet, cylindrical magnet. This also I have shown you in school. So if you drop it, then it is falling, when it is falling through the PVC pipe, it will take normal time, that is as if it is falling freely, like this. So whatever time it will take to fall through a height edge, the same time it will take to falling through the PVC pipe. Now when the same cylindrical magnet is allowed to pass through this metallic pipe. Now this is metallic pipe, and now we are allowing the magnet to pass through this cylindrical pipe. Then what will happen? So now it will take some more time, maybe 1 minute to cross this pipe. Why it happens? Because if the magnet is falling through this metallic pipe, so this metallic pipe may be considered a number of rings placed one above the other, and then this north pole is going inside, so the magnetic field linked with each turn is changing. Magnetic field is changing, so flux linked with the pipe will change. So because of change in flux, eddy current will produce, and that eddy current will oppose the motion of the magnet. So now the magnet is not falling like a freely falling body, because its motion is opposed. Now it is not falling with the acceleration due to gravity. Then some force is there in upward direction because of the eddy current. I mean north, if it is north pole is coming, then here north pole will develop, and then north will repel the north. So north will repel the north. Current will be in anti-clockwise direction, and then this north will repel the north. So its motion will be opposed. Okay, if the weight of the magnet is more than that force, this force, then the acceleration will be less. It is not then falling with the acceleration due to gravity. Okay? So this also you can observe if you have a copper pipe or aluminum pipe, and you have a metallic, I mean this cylindrical magnet, allow it to fall through the metallic cylinder, you will observe it will take 1 minute. Sometimes it will be 1 or 2 minutes depending upon the length of the pipe. But if you allow the magnet to fall through the same height like this, then it will take normal time, that is for a freely falling body, whatever time it will take. T is equal to how much? S is equal to half Eddy square, so half GT square, so T is equal to 2H by G under root, that much time. But if the same cylindrical magnet is passing through this cylindrical pipe, then it will take some more time. Why it is taking some more time? Because of the eddy current, and that eddy current will oppose the reason. Reason is, since magnet is falling through this pipe, so it will oppose that reason, and so the motion will be slowed down. It will fall slowly. It will take a few minutes more. So that's the reason. These are the experimental demonstration of eddy currents. Okay, now we are solving a beautiful numerical based on, yeah, take a snapshot. Snapshot. Okay, I'm writing here metallic ring, metallic disc, metallic disc. Okay, take the snapshot, take it. Then normally 1 marks, 2 marks question will come from this portion. Short answer type question, not a big question, small short questions. So why it happens? What is the reason behind it? A magnet falling through a metallic pipe is obstructed. The motion is obstructed. Why? The reason is eddy current. So this type of question will come. Now, the numerical we are discussing, you have magnetic field. This is not the numerical based on eddy current. Rather, we are discussing the numerical since it is very interesting and is done in your textbook. And you have this rail, metallic frame you can say. This type of frame you have. Okay. And this is x0. Magnetic field is extended up to x is equal to b. And then finally this is x is equal to 2b. Okay. Now, one metallic rod will slide over this rail. You can slide it. Okay. And this magnetic field is acting in vertically upward direction. Dot 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 means vertically upward. Vertically upward direction. And this metallic rod is pulled with velocity speed v, constant speed v, towards right. And then it is brought back to this position. So first it is pulled towards right. Say it goes up to x is equal to 2b. And then it is brought back. Okay. Now initially it is, you are pulling it towards right and then right to left. So finally it will come to x is equal to 0. Now the question is, you have to write the expression for magnetic induced EMF. Write the expression for the first part is induced EMF. Induced EMF in the rod. The second bit is magnetic flux, phi. Then third expression is force acting on the rod. And the fourth part is power dissipated as heat. Fourth factor. So you have to first write the all four expression. Induced EMF in the rod. So rod has length L. Okay. Now induced EMF. You know, induced EMF in the rod is BLV, when magnetic field, length and velocity, all the three are perpendicular to each other, then induced EMF E is equal to, the answer I am writing here, induced EMF E is equal to BLV. But this induced EMF will be constant because you are pulling the rod with constant V. And this will exist only up to x is equal to b. After that, it will disappear. Because now within this portion, there is no magnetic field. So if magnetic field is not there, and if you are pulling the rod in the absence of magnetic field, then there is no question of induced EMF, which is motional EMF, which is BLV. So induced EMF will disappear in this portion, that is in right portion, that is x is equal to b to x is equal to 2b, no induced EMF. So induced EMF will 0 in the region x is less than b and then 2b. That is, the value of x lies between b to 2b, no induced EMF. Now think about the scenario. Now this exists only between x is equal to 0 to x is equal to b. So this is the scenario when x lies between 0 to b, to B means between 0 to B, induced EMF is BLB only. But beyond that, there will be no induced EMF. In figure, no, X means the rod is initially lying here. You are pulling it towards right. Okay. So let this distance be B. So magnetic field extends up to the distance B. After that, no magnetic field. So again for the distance B, there is no magnetic field. And then you return it back. So you are pulling this rod towards left. Now when you bring it back, then what will be the scenario? So this is first bit. Now think about second bit. In second bit, say what is magnetic flux? So flux is equal to, yeah, who can tell me the flux? Magnetic field in strength is B only. That's why we have taken B. So flux is equal to, phi is equal to, yeah, B into A. So B and A is L into this B, L into B. So magnetic flux is increasing, not constant. So it is BLX, BLX. If I ask you what is the magnetic flux when the rod is at this position, your answer will be BL, this is B, magnetic field, then L into this length, that is B, BLB is the magnetic flux. Now after that, magnetic flux, because of this area, there will be no magnetic flux. But magnetic flux up to this portion is BLB, because magnetic flux is B into A. And how will you find area? Area is length into breadth. Length into breadth. So this area, X, yes. So when you keep on pulling this rod towards right, the moment it comes to this position, now X becomes equal to B. X becomes equal to B. So magnetic flux goes up to maximum, that is BLB. BLB. But beyond that, what will happen? Beyond that. Now think, magnetic flux, this much portion is still there. Suppose you are at this position. So magnetic flux of this portion is BLB plus flux due to this portion is 0. Because no magnetic field exists within this region. Okay, area is increasing, but since magnetic field is not there, so that's why no question of magnetic flux. So magnetic flux will remain constant. That is BLB only. So up to this region, magnetic flux now increases, becomes maximum to this portion. After that, that value will remain constant. Though the rod is going towards right, but the increase in area is there, but no field is lying within this right region. So no increase in magnetic flux. Magnetic flux will remain constant. So magnetic flux is only BLB. Yeah, clear? Then think about the third portion, force acting on the rod. So force acting is, yeah, so some current will flow in the rod. Now can you tell me which end of the rod will be negative potential and which end will be at positive potential? Yeah, magnetic field is, say, along this direction. The velocity is along this direction. So electron of this rod will experience force along this direction. So this end of the rod will be negative. This end will be positive. So current will flow along this direction. Current will flow along this direction. Positive to negative. So some current will flow. Okay. Current will flow. Now because of the current carrying conductor placed in magnetic field, it will experience force. And that force is BIL. Force on current carrying conductor. So how will you give the direction of force? Yeah, tell me. This is, current is along this direction. Velocity is FBI. Yeah, B is along this direction. Current is along this direction. So force on the conductor is towards left. Towards left. Are you getting my hand? Yeah, this is magnetic field towards the observer. This is the direction of current. This is the direction of current. So magnetic field along this direction, current is vertically downward, you may say. So force will be towards left. So this conductor will experience force. And that force is given by F is equal to B I L. B I L. Now how can you give I? I is equal to induced EMF divided by resistance. Divided by resistance. That I will give you. The induced EMF B and induced EMF is C. This E by, if resistance of this portion is R, rod is R, then B E R divided by L. Actually not the resistance of rod, actually you have to take the resistance of this whole portion. But if you consider this portion has no resistance and only this portion has resistance, then the resistance of this part. So this is B E by R into L. Now you can put the value of E also. So this E is equal to how much? Yeah, B L V into B L V for E, B L V by R into L. So it's how much? B square L square V by R is the force. This is a force. Force. And what should be the direction of force? Force will be in the left direction. And why the magnetic field? I mean current is in clockwise direction. See, the external field is upward. Okay? External field is up the plane. So the field due to, if you consider this one as a loop, then the field of this loop should be in the downward direction. Downward direction. Because when you start pulling this rod towards right, magnetic flux linked with this portion that also keeps on increasing. According to Lenz rule, the induced current will be such that it will oppose the increase in magnetic flux. So then how it will oppose the increase in magnetic flux? By setting its own field opposite to the external field. External field is in upward direction. So the field due to the loop will be in downward direction. And that's why current is in clockwise direction. See, clockwise direction. Clockwise direction. Yeah? Why flux is increasing? Because you are increasing this area. You are increasing this area. So area of the loop bounded will increase. So increase in area will increase flux. Okay? So this is the force. Third part. And the fifth part is, fourth part is that power. Power is equal to F into V. So F is what? B square, L square, V by R into this V. So this is B square, L square, V square by R is the power. Okay? Now the main part of this is plotting graphs. Now plot the graph of all these quantity. Graph of the above quantity. So I have to rub this portion. I have to rub this portion. Then only I can make the graph. Yeah. Take it quickly. Take it quickly. Because I have very less time to finish this. Done? Okay. So I am rubbing this portion. Okay. Assuming that in one figure I am making all these graphs. 4 graphs will be there. So this is x0, B to B, B to B, then B, then 0, finally 0. Yeah, x0, B, up to this B. The magnetic field is extended up to this portion only. Okay, so this is B. Once again, I am drawing the figure. So this end is P, this end is Q, this end is P, this end is Q. P is negative, Q is positive. Okay, so this is B, x is equal to B. Then the moment you are here, x is equal to 2B. Then when you come back, if you bring the rod towards left, then at this position, this is again B. And then when you bring the rod back to this initial position, then it will be 0. X becomes 0. So what will be the graph of, the first graph is induced, that is B L B flux. Draw the graph of flux, magnetic flux. So flux will be, first the flux will increase. See, y and y-axis flux, you are taking y-axis flux and this axis x. Okay, we are plotting flux. Then we will plot induced EMF. Then we will plot force and then we will plot power. Okay, so we are plotting. You can make it separately, but we are drawing it in the same graph. So flux, see, if you pull the rod towards right, then the area bounded by this portion is keep on increasing. So if the area is increasing, means flux linked with the coil is increasing. So flux is increasing linearly. So up to B it will increase. And then what will be the value of this peak? Peak of flux will be, should I rub it? Yeah. That maximum flux is equal to BL, B only, B into A. So A maximum is B into B, B into L into B. This is B, this length is B. Okay. So flux increases linearly and then becomes maximum at this position. Now after that, area bounded by the loop will increase, but the magnetic field is not there, so there will be no increase in magnetic flux. This means magnetic flux will remain constant up to this position, and then when you come back again this area is decreasing, but no magnetic field within this region, so magnetic flux will remain constant up to this position, up to this B. Now when you bring it towards left, now the area bounded by the loop is decreasing. So the flux also keeps on decreasing. So the flux is decreasing. And the moment you are at the initial position x is equal to 0, this rod is just touching this last end, then area bounded here will be 0, so no question of flux. Okay, am I clear to you? This is the drawing of flux, variation of flux with x. Variation of flux. Now if you want to draw the induced EMF, see, induced EMF will be there because flux is changing. In the region where flux remains constant, there will be no question of induced EMF. So it is very much clear that within this region there will be no induced EMF because flux becomes constant. And d phi by dt, induced EMF will be 0. So within this portion, flux is increasing, and so the induced EMF, this will start from negative. See, this end is negative, this end is positive. So induced EMF, we are drawing it like this. Okay, up to this portion, then it will decrease 0 because from this position the flux remains constant. So no question of induced EMF, no question of induced EMF up to this region. No. Now the flux starts decreasing. If increasing flux is setting the induced EMF in this way, then decreasing flux will induce the EMF in an opposite manner. So the induced EMF will be positive. This part now. So why it is negative? Because see, this P end is negative, this end is positive. So if I ask you what is the direction of induced EMF, your answer will be immediately this side is negative, this side is positive. So we will start from negative only, negative EMF. And the value of induced EMF, we have already written BLV now. So you are taking induced EMF. This is minus BLV, this portion. This portion is negative, BLV. And then it will be remain 0 up to this position because there is no change in flux. And then in flux is decreasing, so induced EMF will be positive. Then what will happen? When you bring this rod back towards left, then what will happen? The polarity gets reversed. Polarity becomes reversed. Now this will be positive, this will be negative. Then induced EMF will be positive. And then the moment the rod will touch this end, the induced EMF becomes 0. Induced EMF becomes 0. So are you getting this graph? Whatever is this negative peak, this positive peak will have the same value. Same value. Now this graph, this portion you are talking, negative part, because the induced EMF in the rod is, see the polarity, the end P is negative and Q is positive. So if you have a battery like this, if I ask you what is the EMF of the battery, your answer will be minus E. It will not be plus E. But if the battery is placed like this, and if I ask you what is the EMF, then your answer will be plus E. Am I clear to you? Yeah? You are starting from negative now. So that's why negative end. Negative. And then within this region flux is constant. So no induced EMF. And then again flux starts decreasing. So if increasing flux is inducing EMF negative, then reducing, that is decreasing flux will induce the EMF in a opposite manner. So what is the opposite of negative? That is positive. And then this peak will have the value, BLV only. BLV plus BLV. Now think about the force. Since force acting on the rod is towards left, so again you will draw the curve from negative side. So from negative side, okay, so up to this portion force will be there, and that force will remain constant, because see the expression for force. Force is equal to, yeah, tell me the expression for force. F is equal to, who can tell me? F is equal to BI, no, not only BI, BE by R into L. The moment you put the value of E, then what is your answer? This is B, E is BLV into L by R. So it's how much? B square, L square, V by R. Now if V remains constant, this V, velocity, speed of the rod by which you are pulling it towards right, that remains constant, then force acting on the rod, that will also remain constant. Force on a current conductor plus in a magnetic field. So force will also remain constant, but force is towards left, that's why we are drawing the graph from left side, I mean negative portion. And then the moment you are out of the field, magnetic field, now no question of current, no question of induced EMF, then no question of current, no question of F is equal to BIL. So no force. So no force is there. No force is there. Again, in this region, the force will be there and towards right. If you bring the rod back towards this end, then the force, direction of force will be towards right, because the direction of current will be reversed. So while going towards right, the direction is from P to Q, and when you bring it back, then direction will be Q to P. And if the direction of current changes, then the direction of force will also changes. So then force will start acting towards this direction. So then it will be positive. And what is the value of force? This is, tell me the force. Yeah? Yeah, this one. B, L square, B square, L square, L square, V square by R. And this one is exactly positive. Okay? Now this is force. This is X is equal to 2B and I am plotting this graph. This is force. And similar is the graph for power. But remember, power will never be negative. So power starts from positive, then it will be 0 up to this region 0, no heat produced, no current, and then in this region it is. So it is positive only. This part is positive. So how can I write this portion? I am writing for this force, yeah, B square L square V by R. This is force, negative value, and this is positive value. And for power, this is power. Power. The formula for power is, yeah, B square L square V square by R. And this will be positive only. No power within this region. Then again power is consumed. Okay? Is it clear to you? B square L square B square by R. This is done in your textbook, NCERT textbook, example, and has been asked many times in board examination, and highly conceptual. Okay? So concentrate yourself on this problem. It is very interesting problem, and that's why I have done it purposely, to make the clear understanding of induced EMF and current and the graph plotted. Okay, just take the snapshot.